Okay, hello Chem II class. This is the study guide review. Of course, we don't have enough time for me to do this during class, so that's why I'm going to do it now. I'm recording it, and you guys can look at it at your leisure. So yeah, I guess I should go ahead and start. Let's see what we got here. All right, let's do that. I'm gonna put that right there. I think I'll put me right here. Okay. All right. Okay. All right. So that being the case, let me go to start with number one. So number one for chapter 13. So this is going to be, of course, a chapter 13 study guide review. All right. So what is the definition of molality? Now, not molarity. Don't confuse molarity with molality. If you recall, molarity is moles of solute per liter of the entire solution. Okay, molality is of course going to be moles of solute, so it's still the same as moles. You still have the same term in the numerator, moles of solute, but in the denominator you have kilograms of solvent. So the answer for number one should be 8, right? Moles of solute per kilogram of solvent, right? All right, now let's look at number two. Number two says if 27.9 grams of lithium chloride is dissolved in 175 grams of H2O, right? What is the weight percent of lithium chloride in the solution? All right, so we want to find the weight percent. Now, you remember I said instead of saying percent, you can say parts per 100. Okay, so percent is parts per 100, and of course we're going to work a few parts. Well, we're going to work a parts per billion problem, and you might have a parts per million or even a parts per trillion problem on your exam. So percentage problems, even though you had this in high school, is going to help. So I'll read it again. 27.9 grams of lithium chloride is dissolved in 175 grams of water. What is the weight percent of lithium chloride in solution? Okay, now I'm going to go to my. Now, of course, we know that percentage parts per 100. So we know that I have 27.9 grams of lithium chloride. All right. Now the total. So I'm going to divide the fraction by the total. Now the total is going to be 175 grams of water plus the 27.9 grams of lithium chloride. Okay. All right, and then of course you multiply this times 100 to get the percentage. All right, so that of course that's going to be 27.9 divided by the sum of 175 plus 27.9, which is 202.9. Okay, times 100. That's going to give me 27.9 divided by my answer times 100. That's going to give me, let's see, the three significant digits. That's going to be 13.8. 13.8%, right? Okay, so let's see what that corresponds to. That answer, so for number two, that corresponds to C. I didn't know that there was multiple choice. Oh, yeah, 13.8%. Yeah, so that's right. Yeah, it is multiple choice. All right. Number three. Let's take a look at that one. Let me go ahead and erase this. All right, so number three says the Environmental Protection Agency has set a tolerable limit for lead in drinking water at 15 parts per billion. Okay, if you have 1 liter of drinking water, 1,000 grams, how much lead by mass is permitted therein? Okay, so so it's 15 parts per billion. So basically we're trying to find 15 parts per billion of 1,000. So we know our total, all right, is 1,000. All right. So now 1,000 would be 1,000,000,000 parts per billion. Okay. So if I the best way to do this problem is to find 1 part per billion, which is easy since 1,000 is 1,000,000,000 parts per billion. If I take 1,000 and I divide it into a billion parts, I have 1 part per billion. And if I get 15 of those 1 part per billion, then I'll have 15 parts per billion. So it's not that big of a deal, right? So the first thing I'm going to do is I'm going to take 1,000, or 1 times 10 to the 3, and I'm going to divide it into a billion, which is 1 times 10 to the 9. Okay, so of course you don't even need a calculator for this. I'll just use a few more significant digits right here. So because so it's going to be times 10 to the 3 minus 9, and that of course is going to be negative 6 grams. That's going to equal to 1 part per billion, right? Now of course if you want 15 of those, 1.000 times 10 to the negative 6 grams times 15, that of course is going to give you 15 times 10 to the negative 6 grams. Technically this is not in scientific notation. To put this in scientific notation, you need the decimal point to be to the right of the first non-significant digit. So that's going to be 1.5 times 10. Since I'm decreasing this number by moving the decimal point from here to here, I'm going to increase this number. So it's going to be a negative 5. So it's going to be 1.5 times 10 to the negative 5 grams. Okay. All right. Now I know you guys are probably saying to yourself, well, I can't really think my way through this, and I need to use the rubric. Okay. If you need to use the rubric, go ahead and use the rubric. All right. All right. I prefer if you didn't use the rubric. I prefer if you tried to think your way through these problems. But actually, I so seldomly use the rubric that I don't actually remember what the rubric is. So give me a second to pull the rubric up. Let's see what we got here. There we go. And let's see. Let me pull up the rubric. Well, I have it for the parts per trillion, parts per million, but it works the same. So I'll pull that up. Now, so since this is a parts per billion problem, I'm going to put parts per billion right here. And then, of course, since a billion is 1 times 10 to the 9, I'll put 1 times 10 to the 9 right there. Okay, so yeah, you'd have to change it up as you go. So if it were a percent problem, I would put 100 right here, and I would put percent right there. If it's a parts per trillion problem, I would put 10 to the 12 right here, and I put parts per trillion right there. So you guys get the idea. So of course, if I don't get 1.5 times 10 to the negative 5 grams, then I've done something wrong. Now we're trying to find the fraction of the total. Okay, so that's what we're going to try to find. So I'm going to put an X right there. So I'm going to say X. Okay, and let's see what I'm saying. Total, I know that's 1,000 grams, and I'm going to put 1.0 times 10 to the 9 right here. Now, parts per billion, since we're trying to find 15 parts per billion, I'm going to put 15 parts per billion right there. Okay, now, of course, not all the time the fraction of the total is what you're trying to find. Sometimes you're trying to find how many parts per billion or parts per million, so sometimes you're going to put the X right there. If you're trying to find the total, then you're going to put the X right there. So using the rubric is pretty easy. All you have to do is figure out what they're asking for. All right, so of course, I'm going to go ahead and cross multiply. I'm going to say 1,000 times 15 is equal to 1.0 times 10 to the 9 times X. Okay, then of course you divide both sides by 1 times 10 to the 9. Okay, so and then in other words, so 1,000 times 15 is of course 15,000, and 15,000 is 1.5 times 10 to the 4 divided by 1 times 10 to the 9. That's going to equal to 1.5 times 10 to the 4 minus 9 is negative 5. Negative 5 grams. Okay, which is X. Okay, so yeah, if you use a rubric, you're going to get the exact same thing. But like I said, I would prefer it if you guys try to think your way through this. Okay, let's take a look at number, let's see, I'm on number 4. If 2 kilograms, okay, so that's 2,000 grams. of drinking water contains 3.00 times 10 to the negative 3 grams of copper. How many parts per million by mass is there of copper present? Okay, now this time I'm not going to use the rubric at all. You guys should, well, I don't know. I guess I can. All right, 2,000 grams of, well, let me go ahead and erase this. Okay, and I'll erase it right there, and I will put this one up here. Okay, so I have, if 2,000 grams of drinking water contains 3.00 times 10 to the negative 3 grams of copper, how many parts per million by mass is there of copper present? Okay, so we know the total is 2,000 grams, and we know the fraction of the total is 3.00 times 10 to the negative 3 grams of copper. So we're just trying to find out how many parts per million that is. So just like before, what I'm going to do is I'm going to find out what 1 part per million is. Okay, and see how many of those 1 parts per million it takes to equal 3.00 times 10 to the negative 3. All right. So in order to find out what 1 part per million is, all I got to do is take 2.00 times 10 to the 3 grams and divide it into million. So 1 times 10 to the 6. Okay, that's going to give me 2.00 times 10 to the 3 minus 6 is going to be negative 3 grams is equal to 1 part per million. Okay, so then I'm going to say 2.00 times 10 to the negative 3 grams, since this is 1 part per million, times some number x. So how many 1 parts per million does it take to equal 3.00 times 10 to the negative 3 grams? Okay, that's going to be my answer. Right, so all you got to do is solve for x. So it's a simple matter of dividing both sides by 2.00 times 10 to the negative 3. So x is equal to 3.00 times 10 to the negative 3 grams divided into 2.00 times 10 to the negative 3 grams. Okay, so of course 3 halves is 1.5. So 1.5 times 10 to the negative 3 minus a negative 3. So negative 3 plus 3 is 0, and 10 to the 0 is 1. So my answer is 1.5. So it's 1.5 parts per million. Okay. All right, and if you want to use the rubric, you can. Of course, since we're trying to find the parts per million right here, you just put an x right here for parts per million. The fraction of the total would be 3.00 times 10 to the negative 3. The total would be 2,000. And then, of course, since this is a parts per million problem, we keep the 1.0 times 10 to the 6. And you simply solve for the x, which would be the parts per million. You should get 1.5. Okay, number 5 says 6.50 times 10 to the negative 7 grams of arsenic is said to be 14.2 parts per billion of a certain mass of cow's milk. What is the mass of this cow's milk? All right, so now we're trying to find the total. We're trying to find the total mass. Now the total, now this is 6.50 times 10 to the negative 7 is 14.2 parts per billion. Now again, you want to find out 1 part per billion. So if 6.50 times 10 to the negative 7 grams is 14.2 parts per billion, if I divide 6.50 times 10 to the negative 7 by 14.2, then I have 1 part per billion. Okay, so how does it help us? Well, if I have a billion parts per billion, then I have the total. So that's what I'm going to do. I'm just going to get the total that way. Alright, so I'm going to say 6.50 times 10 to the negative 7 grams divided into 14.2. Let's see what we got. 6.5 exponent negative 7 divided into 14.2. Let's see what that is. So I ended up with 4.577465 times 10 to the negative 8 grams. That's equal to 1 part per billion, right? So I'm going to take 4.577465 times 10 to the negative 8 grams. And I'm going to get a billion of these. 1 parts per billion. So multiply by 1 times 10 to the 9. And I will have my total, a billion parts per billion. So that number times 1 exponent 9. Okay, and what, that would be 45. Let's see how many significant digits. This is good too. It's good to 3. So it's going to be 45.8 grams, right? So the total would be, or a billion parts per billion would be 45.8 grams. All right, and let's check to make sure that's right. That's number 5. So number 5 should be 45.8. Yay, we were right. It was 45.8. Okay, so let's see number 6. Okay, which of the following statements are correct? Okay, solubility is defined as the concentration of solute in equilibrium with undissolved solute. Solubility is defined as the concentration of solute in equilibrium with undissolved solute in a saturated solution. Yeah, okay, that's right. Number 2, if 2 liquids mix to an appreciable extent to form a solution, they are miscible. Yeah, that's true too. 3, if 2 liquids mix completely in any proportion to form a solution, the resulting solution is supersaturated. That, of course, is not true. So we know the answer is 1 and 2, so that would be D, right? Let me make sure that this, what we have right there for 6 is correct. Yeah, that's D. All right, so number 7. The solubility of 1 pentanol in water is 2.7 grams per 100 grams of water at 25 degrees Celsius. What is the maximum amount of 1 pentanol that will dissolve in 2.1 grams of water? All right, so let me go ahead and screen snip this bad boy. All right, I think I'll do 7 and 8 at the same time. Why don't I? I'm going to hit copy. I'll go to my whiteboard. I'll close that. And I'm going to go ahead and clear my canvas. And I'm going to paste. All right. Okay. So let's see what we got here. All right. Okay, so I'll read it again. The solubility of 1 pentanol in water is 2.7 grams per 100 grams of water. What is the maximum amount of 1 pentanol that will dissolve in 2.1 grams of water? Now, I'll do this the way you guys did the proportion problems in high school. Remember you said we know that 2.7 grams of 1 pentanol will dissolve into 100 grams of water. So I'm going to say this is equal to, now I know how many grams of water we have. We only have 2.1 grams of water, and so we don't know the grams of pentanol. Okay, so I'm just going to put an X right there. Okay, so yeah, all I have to do now is solve for X. I know you're saying to yourself, it can't be that simple, right? It can't be that simple. So I'm going to cross multiply. I'm going to say 2.7 grams times 2.1 grams is equal to X times 100 grams. Okay, of course I'm going to divide both sides by 100 because I want X by itself in the numerator. Okay, so let's see. So 2.7 times, 2.7 times 2.1 divided in 100 equal parts. That is going to give me 0.0567 grams is equal to X. Actually, this is only good to 2 significant digits, isn't it? So it's going to be 0.057 grams is equal to X. Okay. All right. So yeah, that was pretty simple, right? Henry's law constant for nitrogen in water is 25 degrees Celsius at 6.0 times 10 to the negative 4 moles per kilogram per bar. And I don't like this question because the Henry's law problem that I worked in class, the pressure was in atmospheres, wasn't it? And the concentration was in moles per liter. This one is in moles per kilogram. Don't let that stop you, guys. It's still going to be, we're still going to use the same basic thing concept. We're going to take the K times the pressure is equal to S. If you want to put a C right there, you can. Some textbooks, they'll use C instead of S. All right, that's fine. You're still going to use that equation. And so what is the equilibrium concentration of nitrogen? Since they asked for concentration, I know I'm going to solve for S right here. When the partial pressure is 586 millimeters of mercury. Now notice the Henry's law constant is the pressure unit is in bars, okay? And they give it to us. They give us the pressure in millimeters of mercury. So the first thing we're going to have to do is convert millimeters of mercury to bars. So let's see if we have that conversion factor, that unit equation up here. I know that 760 millimeters of mercury, if you look right here, is equal to 1 atmosphere, which is also equal to 0.9869 bar. So I can convert that. So the first thing I'm going to do is I'm going to take my 586 millimeters of mercury times 0.9869 bar for every, let's see, 760 millimeters of mercury. All right, so let's see what we got here. 86 times 0.9869 divided into 760. That's equal to 0.76, let's see, 0.9518 bar. Okay, remember we want to use a whole bunch of significant digits till we get to the end and then truncate it to the correct number of significant digits. Okay, so now I'm going to solve for S. I'm going to say S is equal to 6.0 times 10 to the negative 4 moles per kilogram per bar. Okay, times 0.760918 bar. Okay, all right. So S is going to be equal to, let's see what we got here. So I'm going to multiply my pressure in bars times 6 times 10 to the negative 4. And I end up with 4.5657 times 10 to the negative 4 moles per kilogram. And let's see how many significant digits this is good to. It's good to 2 significant digits, so I'm going to make this 4.6 times 10 to the negative 4 moles per kilogram. That's my answer. That's going to be S. And let's see what we get here. And they don't give me what the answer is in molarity. That's moles per liter. Okay. Oh yeah, it'll be the same. Because guys, remember the density of water is going to be 1 gram per milliliter or 1 kilogram per liter. And I know you're saying to yourself, well, you got nitrogen in it, so it's not pure water. It's not, but yeah, the concentration of nitrogen is so low, it's not going to change it much. So the answer would still be the same. It would still be 4.6 times 10 to the negative 4. So the answer would be C. All right. So I'm going to go ahead and clear my canvas. And let's go back to, let's see, so I'm on number 9 now. Let's see. Which actions will decrease the equilibrium concentration of an inert gas such as nitrogen in water? Okay, 1, decreasing the temperature of the water. Now, if you guys recall, so the question asks, which actions will decrease the equilibrium concentration? All right. Now, gases work differently than solids. Okay. Notice the hotter your liquid, the hotter your solvent, the more solid you can dissolve in it. Okay. Gases work just the opposite. So the hotter your liquid, the less soluble gases are. So since we want to decrease the equilibrium concentration of nitrogen, then we would increase the temperature, not decrease it, right? So the answer would not be 1. Okay. 2, increasing the volume of the water has absolutely no bearing on concentration whatsoever. Number 3, decreasing the pressure of the gas above the liquid. Yes. So that it goes back to Henry's law. Remember, Henry's law says the greater the pressure of the gas above the liquid, then the greater the concentration of the gas in the liquid. Okay, so that's the answer to this would be 3 only. So that would be number 9. For number 9, it's going to be C. Okay, number 10. What partial pressure of oxygen gas is required in order for 0.00284 grams, which is 8.875 times 10 to the negative 5 moles, of the gas to dissolve in 15.9 milliliters of pure water? All right. Let me see. I'm debating whether or not I want to screen snip this. I guess I can screen snip it. I'm going to copy that. And I'm going to go to my whiteboard and I'm going to hit paste. Okay, so what partial pressure of oxygen? So we're trying to find the partial pressure of oxygen is required in order for 0.00284 grams, or 8.875 times 10 to the negative 5 moles, of the gas to dissolve in 15.9 milliliters of pure water. The Henry's law constant for oxygen is 1.3 times 10 to the negative 3 moles per liter. So again, well, they don't give us everything we need, because if you guys recall, Henry's law constant is S is equal to K times P. We're asked to find P. They gave us K. They gave us Henry's law constant, but they did not give us S. But they gave us the means to find S. Remember, S is going to have units of moles per liter. Okay, in this regard, because the Henry's law constant is in moles per liter per atmosphere. Okay, so remember, if you guys recall, molarity, or it has units, it's moles of solute per liter of the entire solution. They didn't give us the volume of the entire solution. They just gave us the volume of the water, what dissolved in. But the volume occupied by the oxygen is so small relative to that of pure water. For all intents and purposes, the volume of the water and the volume of the solution are the same. So all I have to do is, to get the molarity, is take 8.875 times 10 to the negative 5 moles and divide that into 0.0159 liters. Of course, you want to convert your milliliters to liters. Of course, this is a molarity problem. 8.875 times 10 to the negative 5 divided into 0.0159. That's going to equal to 5.581761 times 10 to the negative 3 molar. Okay, moles per liter. So of course, I'll go ahead and do my algebraic manipulation now. I know before I plug numbers in, S is equal to Kp, divide both sides by K. I'm going to have S divided by K is equal to P. Okay, so of course P is going to be S, which is 5.581761 times 10 to the negative 3 moles per liter. All right, and I'm going to multiply, divide that by K, which has units of, let's see, 1.3 times 10 to the negative 3 moles per liter per atmosphere. Okay, since I have a molarity in my numerator and molarity in my denominator, they cancel out. I have reciprocal atmospheres in my denominator, which means I have atmospheres in my numerator. So I have the right units, so I know I did this problem correctly. Okay, so when I take 5.581761 times 10 to the negative 3 and divide that into 0.0013 equal parts, I get 4.29362 atmospheres. Okay, now let's see how many significant digits this is good to. It's good to 3 significant digits, so that's going to be equal to 4.29 atmospheres. Okay, yay. All right, so that's number 10. Let's go take a gander at number 11. You have 14.2 grams of glycerol. Molar mass equals 92.09 grams per mole, added to 14.2 grams of water. Okay, what is the mole fraction of water in this solution? Now remember, if you guys recall, mole fraction is a unitless term. We don't have any units. So all we have to do is take the moles. In fact, I think I'll just go ahead and do 11 and 12 at the same time. And I'm going to hit copy and go back to my whiteboard, and I'll hit clear canvas and hit paste. Alright. Alright, so it says mole fraction, so we have moles of the substance in question divided by the total number of moles. That's all mole fraction is. Now, usually when you use mole fraction, you use it with Raoult's law. So you usually are trying to find, well, you're trying to find the mole fraction of the solvent. Okay. So that's the reason why they asked you for the mole fraction of water in the solution. Notice they didn't give you moles, you were given grams, so you have to work a little bit. Okay, so I'm going to take 14.2 grams of glycerol times 1 mole. Since I'm trying to get moles, I'm going to put that in the numerator of my conversion factor fraction, divided by 92.09 grams. I'm going to put that in the denominator of my conversion factor fraction. 14.2 divided into 92.09. That's going to give me 0.154197 moles of glycerol. And then I'm going to do the same thing for water. 14.2 grams times 1 mole divided by, let's see, 18.02 grams. 14.2 divided by 18.02. I love you, man. That's going to give me 0.788013 moles of H2O. All right. Now, so I have moles of glycerol and I have moles of H2O. Now, of course, I want to get the mole fraction of H2O. That's my solvent. We're more concerned with the mole fraction of H2O. So I'm going to go ahead and say 0.788013. That's the total mole of water in the numerator divided by the total number of moles. Now, since I'm going to add these two numbers together, I have to go ahead and express them to the correct number of significant figures. So that's going to be 0.154 moles of glycerol plus 0.788 moles of water. All right, so that's going to be 0.788013. Now, when you're adding these numbers up, of course, the rules to expressing to the correct number of significant digits change, but they're going to be the same in this case, regardless. Because I have 3 digits to the right of the decimal point here, and I have 3 digits to the right of the decimal point here, so my answer is good to 3 digits to the right of the decimal point. 0.154 plus 0.788. So that's going to be 0.942. Okay. All right. So now I'm going to go ahead and take that entire number, 0.78801333, divided into 0.942, and I'm going to express that to 3 significant digits. Okay. 0.837. Yeah, and I don't know why I'm trying to put units right here since it's mole fraction. So that's your mole fraction. That's going to be X. It's a unitless number, right? Okay, so so go back to that, and so that's going to be number. What number was that? Number 11. So I think I did number 12. Yeah, I have number 12 up here too. Number 12 says the vapor pressure of water is 90 degrees. At 90 degrees is 0.692 atmospheres. What is the vapor pressure in atmospheres of a solution made by dissolving 5.8482 moles of glucose in 1,000 grams of water? Assume Raoult's law applies. So I pretty much gave you the answer because I see it's assume Raoult's law applies, so you know you're going to be using Raoult's law. Shame on me. Shame, shame, shame. So I know Raoult's law says the vapor pressure of the solvent in the solution, I'll just say P solution, is going to be equal to the mole fraction of the solvent times the vapor pressure of the solvent. Okay. Right, so that's Raoult's law in a nutshell, and it can get way more complicated than this because sometimes you have multiple solvents that you have to deal with. But yeah, it can get a lot more complicated. But for right now, we're going to keep it like this. If you guys change your majors to chemical engineering, then yeah, you'll see how it gets more complicated. But let's see what we got here. Now it says the vapor pressure of water at 90 degrees is 0.692, so I know what I'm going to put right there. I'm going to put the 0.692. Now the mole fraction, they didn't give it, but we have a way of getting it. So what is the vapor pressure in atmospheres of a solution made by taking 5.82 moles of glucose in 1,000 grams of water? Okay, so the first thing I'm going to have to do is I'm going to convert 1,000 grams of water to moles of water. So I have 1 mole divided by 18.02 grams. Let me see. It appears to be 55.4939 moles. Okay, so my mole fraction of water is going to be 55.4939 divided by 5.82 plus, let me see, this is good too. I have no idea how many, which of these zeros are significant. I'm assuming all 3 of them are significant. So this is good to 4 significant digits. So I'm going to go ahead and put 55.49 right here. Okay, so let's see what I have. I have 55.4939 divided by 55.49 plus 5.82. That's going to be 61.31. So this number is good to 2 digits to the right of the decimal point. So now, all right, so I got 4 significant digits right here total. So my answer looks like it's going to be good to 4 significant digits. All right, so 55.4939 divided by 61.31 is equal to, I think that's, yeah, 0.9051362. All right, that's going to be equal to X, my mole fraction. Now, just be mindful that this number is good to 4 significant digits. So as I work the problem, as it turns out, it's not going to matter because the pressure that they gave us was only good to 3 significant digits. So my answer is going to only be good to 3 significant digits. So I'm going to say P solution is going to equal to 0.9051362. Remember, this is a unitless number times 0.692 atmospheres. Okay, so let's see what I have. 0.692 times 0.9051362 equals, so the vapor pressure of the solution, maybe data goes away. Okay, so now this is only good to 3 significant digits, so it's going to be 0.626 atmospheres. All right, so that's going to be the answer to number 12. All right, you guys follow me? All right, let me make sure that everything is on the up and up right here. Okay, all right. All right, so that's 12. So let's see. Let's look at number 13. Hey, you only got 2 more problems to go. All right, so number 13, what is the boiling point for a solution containing 0.251 moles of naphthalene, a non-volatile, non-ionizing compound? Remember, I told you guys naphthalene, it was found in mothballs. Okay, so we have 0.251 moles of naphthalene in 250 grams of liquid benzene. And the molar boiling point elevation constant for benzene is 2.53 degrees Celsius per molar unit. And benzene has a normal boiling point of 80.4 degrees Celsius at 1 atmosphere. So I think I'll go ahead and screen snip both of those. And let's see what we got here. Right, and I'm going to hit copy, and I'm going to go to my whiteboard, and I'm going to clear my canvas. I'm going to hit paste. Okay, Now they want to know what is the boiling point. So we're trying to find the new boiling point. We're not trying to find the change in boiling point. All right. Now we have, let's see, 3 equations that we need to be mindful of. 3. Count them 3. Now, so I know that, let's see which one I want to put up first. So I know that delta T is going to be equal to the difference in temperatures between the boiling point of my solution minus T of the pure solvent. Okay, then I also know that delta T is equal to my molar boiling point elevation constant, Kb, times my molality. And I know that my molality is equal to moles of solute per kilogram of solvent. Okay, so we're going to use the moles of bathylene, which is my solute, in my kilograms of benzene. They gave us grams, so 250 grams is 0.250 kilograms. I can find my molality. All right, so I'm going to find the molality. Then I'm going to put the molality in this equation, okay, along with the molar boiling point elevation constant, which they gave us right here. And I'm going to find delta T. Then I'm going to put delta T in this equation, along with the boiling point of pure benzene, which is 80.4, and then I'm going to solve for T solution. Now, I know you say, well, why don't you just put it in one big omni equation, Dr. Price? Because, yeah, it gets confusing doing it that way. I don't like doing it that way. I like doing it this way. It's 3 equations. This happens a lot in science, where you have to, get the answer from one equation, put it in another equation, get the answer from that equation, put it in another equation. So that's what we're going to do. So I'm going to go ahead and say my molality is equal to 0.251 moles divided into 0.250 kilograms. All right. So I'm going to say 0.251 divided into 0.250. That's going to give me an answer of 1.00400. Okay, if you want to just go ahead and use that lowercase italic m for molality, you can do that. All right, so now I'm going to find delta T. Delta T is equal to K sub B, or they have K sub BP, which is 2.53 degrees Celsius per mole unit. Okay, and we got a molality of 1.00400 m right here. Okay, of course those little italic m's cancel out, and my delta T is going to equal to 1.004 times 2.53. So delta T is going to equal to 2.54012, and I have to express that to the correct number of significant digits now, because I am adding or subtracting in the next problem. So let's see how many significant digits this is good to. It's good to 3 significant digits, so this is going to be equal to 2.54 degrees Celsius. Okay, so the next problem, I'm going to put 2.54 degrees Celsius in for delta T. The boiling point of the solution is what I'm trying to find, so I'm going to put that right there. The boiling point of the solvent is 80.4 degrees Celsius. So of course I'm going to add 2.54 degrees Celsius to 80.4 degrees Celsius, and I'm going to get the boiling point of my solution. So of course that's going to be 82.94, and it's only good to degrees Celsius. It's only good to 1 digit to the right of the decimal place, so that's going to be 82.9 degrees Celsius, right? So that's going to be my answer. That was pretty easy, right? Yeah, it was. Number 14, what is the osmotic pressure of a 0.2 molar aqueous solution of glucose? Now, if you guys remember, if you forget the equation for osmotic pressure, all you got to do is recall the equation for the ideal gas law. You know that the ideal gas law is P V equals nRT. So I'm going to say P, divide both sides by V. I'm going to say P is equal to nRT divided by V. Now sometimes you have to use it in this form where they'll give you the moles and they'll give you the volume of your solution. Okay, so sometimes you have to use it like this, but most of the time they give you the concentration, which they did right here. So I'm going to say N divided by V, moles per liter, that is your concentration. So you can put a C right here. Some textbooks, they'll use a M, but most will use a C. And then for pressure, some textbooks, of course, will use pi. So this is a lot of times the equation for osmotic pressure that you'll need to use. Now, of course, you're going to have to remember what R is, but we already remember what R is. Okay, now they want to know what the osmotic pressure is, so I'm going to say pi is equal to the concentration, which is 0.200. I'm going to go ahead and put moles per liter right here so you guys can see my units cancel out. Okay, times R, which is 0.08206 atmospheres times liters per mole, my lord, per Kelvin. Master, and my temperature is 298 Kelvin. And like I've said many times in the past, if you use your units, the world is not going to come to an end, and the sky is most definitely not going to fall. Okay, so notice what I have. I have moles in the numerator of my molarity term, and I have reciprocal moles in my R term, so they're going to cancel out. So anytime you see m to the -1, if it's in the numerator, it means you have moles in the denominator. So my moles cancel out. Okay, I have liters right here, and I have liters in the numerator of my R term, so liters in the denominator of my molarity. And all right, so they're going to cancel out. I have kelvins and reciprocal kelvins, so they cancel out. The only unit I'm left with is atmospheres. So all I have to do is take 0.2 multiplied times 0.08206, then multiply that times 298, and I get pi equaling 4.89 atmospheres. Yay! Okay, so that is the chapter 13 study guide, and that took everything out of it, brother. Okay, yeah, so I hope you guys appreciate that. All right, I will, I'll see you.